Good morning.
Good morning, sir.
Good morning, sir.
Morning. So, in the previous class, we discussed about the various models for noise, and we also learned how we can estimate noise by using the assumptions that we have made, and we also discussed about uh, how this noise can be filtered by using a simple averaging filter or maybe a geometric mean filter. Let us continue now with discussions on noise filtering. The slides visible.
Yes, sir.
So the first step is to start with. We will assume that the degradation function is in fact uh, it's an impulse function. That means the point spread function of the degradation uh, uh, block is an impulse. So with that assumption, what we get here, since it is convolution of an image with an impulse, I'll have f of x comma v here, and noise is getting added. So this is just a model where the restoration filter uh, will now work on this type of degraded image. That means the image is degraded only you by in the with the noise. There is no blur. Okay, that is the assumption we are starting with. Now, if you go to the frequency domain, even though this is not defined, that means Fourier transform of a random phenomena is not defined. We use a different method of in fact evaluating it. But the equation looks as if I want to determine the original image, I need to determine the spectrum of that. So I have to take n to the other side. So that means subtracting the noise from the original, from the degraded image, I'll get the original image. This is a simple equation, but all of you know this. This cannot be done because I don't have this directly. So we started with two filters. Arithmetic mean filter, this is something that we have already done under the heading of box filter in image enhancement. Suppose if I take the window size to be say 3 cross 3, then this will be 1 by 9. So we are just adding all the pixels over a 3 cross 3 window and then divide the value by mn. So this is your box filter. If I increase the size of the kernel, the amount of blurring also increases, but definitely the noise would be removed better. This is what we have seen as an example also. An improved version of this filter is a geometric mean filter, where you can observe that instead of adding the pixels as we did here, you multiply the pixels over a specific neighborhood, and then whatever answer you get, you raise it to the power of 1 by mn. So in the previous class I showed you, suppose if the image is a smooth image, that means all the pixels are say 10, this will be 10 to the power of 9 raised to the power of 1 by 9. Therefore you will get the original in fact the actual value of the gray level to be equal to 10. That means smooth data will be passed through the filter. And comparatively, arithmetic mean filter is simplest, and this can be implemented by using simple convolution operation. In this, noise is filtered or noise is reduced at the cost of blurring, but geometric mean filter, no doubt it smooths compared to the arithmetic mean, but it tends to lose less image detail because this is a product, whereas this is a sum. Obviously, the averaging effect will be severe here, therefore edges may get smoothened out here, whereas since this is a product and you are raising it to the power of 1 by mn, it tends to lose less image detail. That means the edges will be better preserved in the second case. That is the advantage of geometric mean filter. Moving on, we have another type of filter called harmonic mean filter. If you observe what is happening here, 1 by GST, that means over a range of your kernel, you just take the reciprocal of each of them and add, and the value that you get divides Mn, and whatever you get is f hat of x comma y. Okay, so this is just an improved version of harmonic filter and sorry, a mean filter. The next one is contra harmonic mean filter, which again works on a neighborhood s of x y, and this neighborhood can be anything. It can be 3 cross 3, 5 cross 5, any neighborhood if you want. So here we introduce a new constant q. Okay, and depending on this q, whether it is positive or not, this type of filter is able to remove pepper noise or salt noise. As we know, in the last previous discussion we had discussed about pepper noise and salt noise. Salt noise is white pixels, pepper noise is black pixels. That means okay, an isolated black pixel or an isolated white pixel is an impulse type of noise. So if I want to remove pepper noise, you have to use positive Q here. If I want to remove salt noise, you have to use negative Q here. Now, typical values of Q, if you just substitute here, for example, when Q is minus 1 here, so you know this is minus 1, this is plus 1, minus 1 plus 1 cancels out, so this is 0. Anything raised to the power of 0 is 1. So it would be something like 1 by GST, G of ST to the power of minus 1. So obviously it looks like a harmonic mean filter, because G of ST to the power of minus 1 means it is 1 by G of ST, which would be this. So if, for example, Q is 0, that means if this is 0, this is 0, so this will be 1. This is 0, so it is summing all the values, and this looks like an arithmetic. So contra harmonic mean filter can be used either as a harmonic filter by using Q equal to minus 1, or an arithmetic mean filter by using Q equal to 0, or I can use it to remove pepper noise by choosing positive value of Q, and salt noise by choosing negative value. Harmonic mean filter works well for salt and of course Gaussian type of noise, but fails for pepper type of noise. Even though I can choose positive value of Q, it doesn't remove pepper noise so good. Okay, but for Gaussian noise and also for salt noise, it can be better used. So you have some typical examples here. This is an X-ray image of a circuit board, and what you see here is an image corrupted by additive Gaussian noise. So you know we have made an assumption that noise is additive, and in this case we are assuming that the noise PDF is a Gaussian distribution. Okay. What you see here is the result of filtering with an arithmetic mean filter. Hopefully you can observe that the noise that is present here is removed, and this is by using a geometric mean filter on the same. Okay. So if you carefully observe, particularly observe this portion and this portion here, you can see here the sharpness is less here as compared to the sharpness. In fact, there is a sharp edge at these points, whereas here the sharpness is less. This is what I told you in the previous discussion. So this is a disadvantage of arithmetic mean filter. No doubt it smoothens noise, it has smooth noise. In fact, in both the cases, noise is smoothened. But particularly when it comes to preserving edge information, Gaussian geometric mean filter does better when compared to the arithmetic. So this is to remove pepper or salt type of noise. So in the first case, the image is corrupted by pepper type of noise. You can see black dots. So black dot means it is pepper type of noise. In the second case, in this case, it is salt noise. You can see white dots on the image. So if I use maybe a contraharmonic filter and the value of Q is taken as 1.5 plus 1.5. So when I take positive value of this Q, it can remove pepper noise. So you can see the noise is removed. If you take Q is equal to minus 1.5 on this, it can remove the salt noise. So this is a demonstration how you can remove salt or pepper noise by carefully choosing the value of Q. Suppose this is an obvious thing, if you take wrong choice, okay, so if you use Q is equal to minus 1.5 and try to remove the pepper type of noise, obviously instead of improving the image or removing the noise, it has spoiled it. Similarly, if I take positive value of Q in case of salt type of noise, you can observe that it is going to corrupt the image rather than improve. So choice of the value of Q is very important. First of all, the positive or negative value is very important in actually removing the required type of. Okay, so if you remember during the second unit, we also discussed about what is known as ordered statistics filter. Okay, so the principle of working of this is based on ranking the pixels or ordering the pixels. Okay, and now these type of filters are useful for impulse type of noise, which can be unipolar or bipolar. Unipolar means one type of noise, either salt type or pepper type. Bipolar means both salt and pepper noise will be there. Okay, um, so again we have discussed this, but we are repeating it and we are adding two more filters. One is a median filter, second one is a max per min filter, third one is a midpoint filter, fourth one is an alpha trim mean filter. Okay, so can anybody tell me how does this median filter work? Can I just, because we have done this, what is the principle behind median filter? For example, I want to apply a 3x3 median filter. How should I do it? What is the procedure?
Sir, it will replace the value of a pixel by the median of the intensity level in the neighborhood of that pixel.
No, like, can you elaborate? Median is correct, but what do we mean by median? What should I do? Suppose if I assume that there are 9 pixels in that window, what should I do? Well, the answer is there. What is to be done?
Sir, first sorting all the pixels.
Yeah, so you have to put all these okay, pixels under the window in an increasing order, then pick the middle of that, which becomes the median of the values. Okay, so that's what you do. Obviously the salt and pepper noise, salt noise means it is nearing 255, pepper noise means it is nearing 0. So when you arrange all of them in an increasing order, 0 or your pepper noise will be to the left and salt noise will be to the right extreme point. So when I pick the middle of them, you are sure that you are going to remove salt and pepper type of. Similarly, max or min filter, arrange them in an increasing order, pick the maximum value, arrange or pick the minimum value to get the min filter. Okay, so that is what it means. median of the values in that particular neighborhood, max of the value in that neighborhood, min of the value in that neighborhood. Midpoint, as the name itself says, you will take the maximum value, you will take the minimum value and find the midpoint. That means just take the average of them and whatever you get, you replace it. This is a midpoint filter. Alpha trimmed mean filter is an adaptive filter, very close to an adaptive filter. What we do here is, even though we have a kernel size of say xy, the size to be say m cross n, you will not take all the values in taking a decision. You will only take values mn minus d, where d is decided by the user. So what you will do is, you will just take only the middle mn minus d pixels, add them and divide it by mn minus d. So I don't apply the filter for the entire mn. You are actually taking the values only very close to equal to mn minus d, add them. That means the center pixels. For example, if you have a 5 cross 5 um, filter to be applied, maybe I'll take only the central 3 cross 3 region and then apply the filter. That is how alpha trim mean filter is done. That means you are going to delete the d by 2 lowest and the d by 2 highest gray level pixels. That means I don't use the entire uh, uh, neighborhood. I will just take the central portion. Okay. So I think the demonstration is done here. This is an image corrupted with salt and pepper type of noise. I hope you can notice black and white pixels on the image. This by applying median filter one time. That means one pass. I just apply the median filter one time, and this me I am applying the filter once again. Result of processing with this filter, and then this you apply the filter again. Now carefully observe. Can anybody comment? I'll just show the region where you have to see also. Just try to see these regions. I don't know on your computer, on your laptop or mobile, it is visible. If I repeatedly keep applying median filter again and again, what happens is, no doubt, if there is any salt or pepper type of noise, it removes. But after one or two times, if you keep applying it, you will start losing the edges also, because the filter starts looking them also as a salt and pepper type of noise. Okay, so you can, in fact, this is a very good simulation that you can try at home. You can use MATLAB to do that. Take an image, add salt and pepper type of noise. You know the command to do that. Apply median filter once, apply twice, apply thrice, and start observing that after I start increasing the number of times I am applying the filter, you will start losing the edge information. Okay, so this is why we don't use median filter more than normally twice. Okay, this is by using a max filter, and this is by using a min filter. Okay, so uh, you can observe that max filter, it is going to remove the pepper type of noise. Min filter is going to remove the salt type of noise, obviously, because when I arrange them in an increasing order and take the max value, obviously the min value is going to be removed. That means the black pixels are going to be removed. So that means I'll be removing the pepper type of noise. Similarly, if I apply a min filter, I'll be removing the salt type of noise. Okay. As I said, the the filtering that is happening, that means the noise that is going to be removed, is always at the cost of blurring. That means if I apply an average filter, or if I apply a mean filter on an image, no doubt it is going to remove noise, but it is also going to smoothen the edges. So to take care of this smoothing of edges, we normally use what are known as adaptive filters. These are depending on behavior of the characteristics of the image in the region. That means I don't simply apply the filter without looking at what are the pixel values appearing there. Definitely, it has improved performance, but at the cost of increased complexity. Because since it has to adapt to the local behavior for every time when you are applying this filter, you need to make some calculations. Okay, let me explain an adaptive local noise reduction filter, which uses mean and variance as the measurements. Okay, what it does is at every time when I am trying to apply the filter, it tries to find the local mean, it tries to find the local variance, then compare these values with the probably the variance of noise and take a decision based on this local mean and local variance. Okay, I repeat, whenever you are trying to calculate the new pixel value by using this adaptive filter, earlier we were applying the filter directly without looking at what is the value. So now what we do is try to first find the mean in the region, try to find the variance in the region, and you know how to find the local mean. Okay, I think probably that formula is somewhere here only. Let me just show it. Okay, so you can, this is a formula to use to find the local mean. That means over the kernel size, find the probability values, and you also know how to get the probability value of the gray level. Just count how many pixels are there, count how many times each pixel is repeating. So the number of times the pixel is repeating divided by the total number of pixels will give me the probability. So that probability multiplied by the actual value summed up in that region will give me the mean value, and by using this formula we can find the variance. So find the local mean and the local variance, and then apply this algorithm. Okay, what is algorithm? This is what you have to do. Please understand the equations here. F hat of x comma y is the in fact the restored image pixel value. G of x comma y is the original pixel value at that particular position x comma y. Sigma n square is the noise variance. So we are assuming that noise variance is available with us, or we can estimate this. So we have discussed how to do this in the previous class. Noise variance can be obtained by just using the method which we have already discussed. Sigma L square is a local variance, and I just showed you how to find the local variance of the image. ML is the local mean. Okay. Now observe here, this is what you are supposed to do. Okay, one by one let me just explain. Suppose if the noise variance is 0, that means there is no noise at all. Obviously when there is no noise, you have to just return the actual pixel value, because since it is not a noisy pixel, I don't need to do any filtering. If the local variance is greater than the noise variance, can somebody tell me what is the situation when this can happen? When the local variance is greater than the noise variance. Anybody? When will you expect the local variance in a region of the pixels is greater than the noise variance? Where you can expect the variation to be more? Anybody? Okay. Nitin is telling edges. Yes, correct. Good. Okay. So near the edges, local variance will be more than the noise variance, obviously, because near the edges, pixel value will be changing a lot, so the variance will be more. Now whenever the local variance is more than the noise variance, It means that I am near the edges, and I need to preserve the edges in an image, because that is the whole in fact objective of using an adaptive filter. So when that is the case, when the local variance is more than the noise variance, you are not supposed to do any filtering. That means I have to just return a value close to the actual value available there, because that would be an edge pixel. So you are not supposed to smoothen it. Okay. Now when the local variance is same as the noise variance, that means there is a noise there. What you need to do, you have to just average that noise and give me the uh, value equivalent to the mean. So that is why you have to return the mean of the value, because you need to remove the noise there. That means you need to average it. I repeat, when the noise variance is 0, return the gray level value as it is. When the local variance is greater than the noise variance, return a value close to the value g of x comma y, because you need to preserve the edges. When the local variance is same as the noise variance, return the value, arithmetic mean of that value. Okay. So now observe the formula here. Let us apply these conditions and see whether that is happening. Noise is 0. Sigma n square is 0 means numerator is 0 here. So that means this whole term is 0. Your f hat, the new pixel value, is same as the original pixel value. As you can see, that is what you are supposed to return. If the local variance is more than the noise variance, that means the denominator is greater than the numerator. So that means this term will be very small. So a very small value multiplied with this, you will get a very small value here. So I am subtracting a very small value from g of x comma y, which means that you are returning a value very close to g of x comma y. May not be exactly g of x comma y, but very close to it, because this ratio is very small. Therefore, this whole term is very small. And look at the third one, when both the variances are same. That means these two are same. So you can cancel them out. Minus g of x comma y cancels with plus g of x comma y. Minus of minus will be plus ml. So your f hat of x comma y will be equal to ml. That's exactly what you are supposed to do. Okay, so I'll assume that you have understood this adaptive behavior of the noise filter. If there is any question, you can ask. Otherwise, we'll continue. This is an adaptive local noise filter. Any doubt?
No, sir.
Oh. So what is understood here is by just using the local behavior. But what is it we are paying here? See, if I had to use a simple median filter like this, or sorry, mean filter like this, you can just perform convolution. That means I just take an image, convolve it with the kernel. But now, every time when I go to a new pixel position, every new pixel position, I need to calculate the local variance. I need to calculate the local mean. Of course, noise variance is already known, you have estimated, so you have to do it only once. Whereas the local variance and also the local mean, I have to estimate it at every pixel position. So which means computationally this is complex. Definitely it is complex. That is what is written here. Increased complexity. Okay, but the performance improves because you are not simply removing the noise, and you are also blurring the image. You just look at the noise value and compare it with the variance and taking a decision adaptively based on the algorithm. So obviously this would help in preserving the edge information, at the same time smoothing the noise at the cost of okay, high computational complexity. The performance would be better. Okay, so these are some results shown. This is image corrupted with additive Gaussian noise of zero mean and variance some 1000. This is result of arithmetic mean filtering. So you can observe that no doubt the noise that you see here is removed, but also observe that these were sharp here, whereas they are now blurred here. And this is applying a geometric mean filter. This also is not doing that great, even though we said geometric mean filter can preserve edges, but it is not doing so much, as we can observe this region and this region. Now look at this adaptive noise reduction filter, and actually is using a 7x7 filter kernel size. Now carefully observe this portion and compare it with the original here. The sharpness of these, okay, structure is retained, which is not there in these two filters. So this will demonstrate that by applying an adaptive filter, I can remove noise, but at the same time I can preserve edges. Okay, so in fact there is another adaptive filter called adaptive median filter. I want any one of you to pick up this as a seminar topic and present it. Okay, uh, whoever does this seminar will definitely have some weightage either in quiz, or I can in fact uh, consider this performance for quiz, but only one student can do it. So let me know who is interested. Adaptive median filter, this is what has to be done. Whoever prompts first will be given opportunity. You have to prepare slides for it, and you have to present it in the class like this in online mode. Slides and explanation. Adaptive median filter. Okay. So this is also a part of the syllabus. So I'm not doing it. I want any one of you to take it up as a. It's available in the textbook. So anybody who is interested can take it, and this assessment will be taken as one of the quiz marks. Okay. So as I said in the beginning, uh, restoration can be done either in spatial domain or frequency domain. Whatever we have done so far here, you can observe that you just looked at the pixel values, that means the spatial coordinates, and applied the filter. All these formulas that we have seen, they are looking at this pixel values, that means the gray level values, or I am applying the filter in the spatial domain. But we saw in the previous chapter itself, you can take the image to the frequency domain and then apply the filters. Okay. Um, what you see here are an example for a band reject filter. Okay, this is only an example. We don't discuss all the filters because we have already done them in enhancement chapter itself. Remember, ideal low pass filter, ideal Butterworth filter, um, ideal Butterworth filter and the Gaussian filter, ideal high pass filter, Butterworth filter, Gaussian filter. We have discussed in previous chapter. So we are not discussing them here. We are only introducing a new type of filter called band reject filter. All of you know a band reject filter means it's a filter that rejects a particular band of frequencies and allows the rest of the frequencies. Now carefully observe, I have already told you that black, uh, okay, in this case actually this portion is actually dark, and this portion is dark, and this portion, there is actually a hollow region. So carefully look at these things. Just because it is dark, don't think that they are blocked. Actually, this is a hollow portion. I hope you can in fact visualize it. This is just like a hollow portion. So this frequencies will be rejected and all other frequencies will be passed. Okay. I can show this in the form of a 1D perspective plot for better visualization. Let me just do that. So suppose if you just have if you just have your 1D representation of the filter, something like this. So let us assume that this is h of f. Is the one node visible?
Yes, sir.
So you know how band reject filter works. It allows this band of frequencies, and it is definitely going to reject a very narrow band of frequencies, like or very band. So this is the stop band, and whereas this is the pass band. Okay, so whatever is in this frequency range is going to be removed. Okay, this is how a band reject filter works. So now visualize this in 2D. That means in a circular region of this nature, you will have frequency variation. So just observe here in this circular region, the noise, whatever is existing in the image will be removed or killed. The rest of the region will be passed. Okay, so this is a hollow region. Be very careful. Even though it looks white, don't think that okay, this region is going. This the frequency values will be allowed. This is actually killed. These region will be allowed. Okay, so you are going to reject these frequencies. This is ideal filter, but there is a disadvantage of ideal filter. Anybody to remember what is the disadvantage of ideal filter? What is the disadvantage of ideal filter? Why did we go for Butterworth or Gaussian filter? This was discussed in the last class. Prajwal BC, can I just respond?
Yes, sir.
Yeah, what is the disadvantage of an ideal filter?
Sir, it introduces ringing effect.
See, why should I ask you? Can you not unmute and speak if you know the answer? You are correct. So ideal filter is going to introduce ringing effect, and we know why it introduces ringing effect because any sharp transition, in the other domain it is a sync. We have seen that a rectangular pulse in one domain is a sync pulse in the other domain. So multiplication with this type of ideal filter, it means that I am convolving the image with a sync pulse, and the characteristic of a sync pulse is it will cross the zero frequency at every regular intervals, and because of this there is there is a ringing effect that is going to be introduced. So to avoid that, what we do is we go for a smooth filter, which is a Butterworth filter or a Gaussian filter. Okay, so of course both of them are going to remove the ringing effect. The advantage in Butterworth filter is I can play with the order of the filter. Actually, in this case, it is first order. Suppose if I start increasing the order of the filter, it starts moving towards the ideal nature of the filter. So I can control the ideal nature of the filter, and also I can make sure that the ringing effect is eliminated. Gaussian filter is a smooth filter. Here you don't have any control. Okay, the only control is the cutoff frequencies. Now, a very good application of this ideal or maybe whatever band reject filter is in removing what is known as periodic noise. Hope I remember this is one of the type of noise we discussed in the beginning of this unit. What you see here is a periodic nature of the noise. Hope you can see that when I start moving towards the right, or when I move towards this, or maybe in the diagonal direction, what you notice is there is a variation periodically. That means the brightness value keeps increasing, decreases, and then increases and decreases. That means this is looking like a sinusoidal signal. a sinusoidal signal along this direction, a sinusoidal signal along this direction, and sinusoidal signal along the diagonal directions. So when I take Fourier transform of such an image, because of the periodicity of these noise, you notice that there are white dots along the direction of the noise. See, there are two white dots. I hope you can notice them. Along this direction, the sinusoidal variation, there are two dots, impulses. Again, two impulses in this direction and two impulses in this direction. Okay. So this is the advantage. If it is a periodic type of noise, I can just visualize it by going to the frequency domain. So I know these dots are disturbing my image, which means only these dots are to be removed. So a good example of a filter which can remove only this frequency range is a band reject filter of this nature. Okay, here the black ring that you see is the region of frequencies that are going to be rejected, and the white region that you see is the region of frequencies that you are going to accept or allow. So this region will be allowed. Only this region frequencies or the region or range of frequencies in this particular ring are going to be rejected. So when I multiply these two, obviously these dots that you have are going to be removed. What is the meaning of removing these dots in frequency region? You already know that these dots are due to the sinusoidal frequency variation you have, the periodic noise that you have. So when I remove that, I'll get back my original image, which is, you can just see that, which is not having any noise in the image. Okay, so the periodic noise can be removed by using this type of band reject filters. Okay, so in this case actually is an ideal filter which is used. So this is the ideal, in fact the output image that you get from this. Okay, so this is advantage of using band reject filter. Actually what they have used is, they have used a Butterworth band reject filter, and as I said, white corresponds to 1 and black corresponds to 0. So these frequencies are killed. Since it's a Butterworth filter, you can also see that there is no ringing effect that is seen in the image. Okay, is this clear?
Yes, sir.
Hello? Okay. Yeah, good. So this is how I can remove noise by using band reject filter. Okay. In fact, other noise rejection filters, since we have already discussed in previous module, we are not discussing them here. Only this filter was not discussed in previous unit, that is why it is introduced here. So band reject filter can remove periodic type of noise, a sinusoidal type of noise. Okay. Okay, so I think this is where probably I'll stop now. The next thing that we are supposed to discuss is uh, how we can in fact estimate the degradation function. Remember, we have estimated noise. So now suppose if the image is blurred with okay, it's blurred with some type of blur, how do I estimate it? So there are many methods to do that. Let us discuss this in the next class.